Welcome to Lesson 12a, Inertial Separation. We're going to talk about inertial separation, how and why particles veer across curved air streamlines. I'll also show you the iteration procedure to solve for the inertial separation speed. Let's consider a particle in curved airflow. For example, a curved duct. Consider an air streamline with some radius of curvature r. Let the airspeed u vector be tangent to this air streamline. This is a vector and its magnitude is u theta. Its direction is in the tangential direction, tangent to this curved air streamline. Let's suppose we have a particle at that location with the normal diameter dp and density rho p. The air has the normal properties rho, mu, and lambda, just like previously. Well, the reason we call this inertial separation is because the particle is heavier than the air, so it gets flung outward with some speed that we're going to call vr. It's a radial speed. It's a velocity in the radial direction. And if we complete the parallelogram, in other words, add the vectors, we see that v moves to the outside of the air streamline. In other words, the particle veers outward at some radial speed vr. This is what we call inertial separation. Note that we assume the particle also moves at speed u or u theta in the tangential direction, as I've sketched. Recall from high school physics, the centrifugal acceleration for a particle moving in a circular path is just u theta squared over r, where r is the radius of curvature as we have sketched here, and u theta is the tangential component. This applies to any particle or a baseball on a string that you're swinging around, as we did in high school. This is an outward force. I put it in quotes because, remember from high school, the centrifugal force is kind of a fake force. There's really a centripetal force that's pulling this particle towards the middle. But from the particle's point of view, it feels like it's being flung outwardly at this acceleration. We're ignoring gravity here. So the bottom line is anytime you have an air streamline that's curved and you have a particle that's initially moving with that air streamline, its path is going to be veering outward compared to the air streamline. Let's consider the analogy between inertial separation and gravimetric settling in a duct. I put the inertial case on the left and the gravitational case on the right. Here's our radius of curvature. Down here is our particle moving at some v theta, which is equal to u, or u theta, and then it's also being flung radially outward at vr. So if this is a curved duct, you can imagine kind of unwrapping this, just bring this part down until it looks like a horizontal duct. We really have the same problem, except in this case, the acceleration is due to gravity. We called that capital VT the terminal settling speed. In this case, it's called little vr, which is the radial separation speed. But these are really analogous problems if you kind of flatten this out and straighten it out to look like this. The only difference is the acceleration is u theta squared over r, whereas here it's just gravity. That makes these problems easy because everything we've learned about gravimetric settling also applies for inertial separation, except we replace g with u theta squared over r, and we replace vt with vr, where vt was in the minus z direction and vr is radially outward. So there's really nothing new to learn here. If you know u theta and if you know r, you can calculate this acceleration. And instead of using g in our equations, we use this, u theta squared over r. And in your program, you could still call it VT if you want, but we're replacing VT with VR as long as you know what it means. VR is this radial separation speed of the particle, whereas VT is the downward settling speed due to gravity. So it's the same equations, the same iteration scheme, everything's the same except for this acceleration term that's replaced. So as I said, that makes our life pretty easy. Let's go back to gravimetric settling, which we already know. Remember this equation that we had to iterate with Cunningham and the Morrison equation for CD and all that. Well, now we can immediately write the equation for inertial separation, where you can see that all we've done is replace this g with u theta squared over r. Everything else is the same. So again, all we've done is replace g with u theta squared over r, and we've replaced vt with vr. Once you do that, you can see that they're pretty much the same equations. So to solve for VR with this equation, I have good news and bad news. Bad news is that you must iterate. The good news, we use the same iteration procedure that we already know and love.
I wouldn't say that I love the iteration procedure.
It's just a figure of speech, Arnold.
Okay.
You already have this set up in your software. Simply replace g by u theta squared over r. And as I like to say, that's all there is to it. Here's a quick review of the procedure. First, you guess VR in meters per second. Calculate the Reynolds number, which would be rho VR dP over mu. We're replacing VT with VR now, so that's the Reynolds number you use. Calculate CD at this Reynolds number using the Morrison equation, and then use equation 1 to get a new VR, where I'll call this equation 1. And just quickly, this is the same problem we had previously where CD is a function of Reynolds number, which is a function of VR. So that's why you have to iterate this as an implicit equation. So you guess something here, you calculate Reynolds number, you calculate CD, you calculate a new VR, and then the trick, like we did before, is to use this as our next guess. Then you calculate a new Reynolds number, a new CD, a new VR, and you use this as our next guess. And you keep doing that, just like we did before. And it converges pretty well. In fact, I've found that this converges even easier because the numbers are bigger than the VT for settling in gravity. Let's do an example problem. Dusty air flowing into a curved duct or an elbow. Particles are flung toward the outside of the duct due to inertial separation. The properties, temperature, pressure, we'll use 50 micron particles. Densities given of the particle. The mean radius of curvature of the duct is 0.225. This is along the duct center line. So if this is our duct and this is our velocity u or u theta, we're defining this as Rm, the mean radius of the duct, and then the particle will be right there and it will fling out towards the outside. Finally, we give u theta itself, which is 10.2 meters per second, average speed through the duct. We're not considering boundary layers again. We're just letting this be some u, especially in the middle of the duct. It's just the velocity we have there. Here's all the equations we need. For the air properties, use your ideal gas law. We use Sutherland's law for mu. We use Cunningham, where we need to find lambda and Knudsen number. This is all review. This is the same equation I had called that equation 1, and I'll use Rm here for the radius of curvature r. And then Reynolds number and Morrison's CD equation. This is the same as we did before, except this term u theta squared over r is the acceleration instead of gravity. It's kind of like a fake gravity term. So let's plug in some numbers. U theta squared over r is u theta squared over rm here at our location. Plug in the numbers, and I get 462.4 meters per second squared, which is an acceleration. Notice how much bigger this is than gravity. If you take this acceleration divided by gravity, this is about 47 times greater than g. So that's a pretty high acceleration. In other words, it's 47 g's. Well, once we have this, we just replace gravity with that and iterate. I used Excel, and here are my results. This may look familiar. It's the same Excel sheet that I had before. Literally, the only thing I did was instead of g, I put u theta squared over rm here. I had to add 2 more cells that I entered rm and u theta, and then calculated u theta squared over rm. And I changed this from VT to VR, but the rest of it's identical. And here's our answer. VR is 6.14 meters per second radially outward. Remember, our u theta was about 10.2. So unlike the particles settling where we always had VT being very small compared to capital U, here they're about the same order of magnitude. In fact, VR can actually be larger than u theta. This is a great way to separate particles from the flow. And we'll find out, for example, with cyclones, which we'll talk about next, we use this inertial separation idea to fling particles to the outside to remove them from a flow. So it's a way of creating an air pollution control device. Now I'll just show you this live in Excel. This is in fact the same file I showed you before. I just didn't scroll down far enough to show you the inertial separation part. But we have all these constants for the ideal gas law and calculating mu from Sutherland, etc. Here are my inputs in yellow: temperature, pressure, particle diameter, particle density. The rest of these are calculated. And this is what I showed you before. I used Stokes' approximation just to compare, and then I plugged in some guess and we iterated using Morrison. I showed you all that before, and I showed you that you can use any guess here and it still works. And then I iterated horizontally. Well, I literally copied this whole thing and pasted it below here. And all I did was add an RM and a U theta. And then I calculate U theta squared over R as my fake gravity, my acceleration. And then the rest was copied directly. The only thing different is I call this VR. So in my Reynolds number, I'm using VR, but I'm using the same air density, etc. from before. The Morrison equation is a function of RE to the left of it in my spreadsheet, so there's nothing different there. And then the new VR is calculated from that equation. You can see up here, it's the same thing except I'm using this acceleration instead of G. And it converges quite rapidly into our 6.14 as I showed you before. And again, this is kind of insensitive to initial guess. Let's try 50. I still get there. Let's try 0.01. It gets there faster if you're close. Obviously, if I try 6, it gets there pretty quickly. But the initial guess isn't that important. It converges pretty nicely, and you should already have this programmed. It's a very simple change to get this to work for the inertial separation case. So I'll say it where you can see me this time. That's all there is to it.
That's all there is to it, dude.
Thank you for watching this video. Please subscribe to my YouTube channel for more videos.